how am I to make sense of this expansion? This is an eigenfunction expansion still, okay? But it's disguised because the k form a continuum. And really, okay, you recognize first of all this is the inverse Fourier transform formula. Okay? But now remember that the other expansion we did. Okay, let me put it in the case where we have a discrete eigenfunction, discrete eigenvalue, or the summation over all of the eigenstates. Right. So now the Cn actually just goes into this Fourier transform, right? And the summation over n, of course, that goes into this integration when the eigenfunctions form a continuum. So a specific shape of this might be, I might be interested in a Gaussian wave packet. And the Gaussian waves and the Gaussian integrals in general are extremely important in quantum mechanics. Okay, so let me use this. Okay, let me use the remaining time to teach you two things. First of all, how do you integrate a displaced Gaussian? And then second thing is, well, what is the specific case of alternating principle illustrated here? Okay, so Gaussian wave packet in momentum space, or in wave number space, okay, it looks like this. So first of all, we like to fix this constant, right? Remember, we need to sum up to 1. Okay. This corresponds to the way the Fourier transform being normalized as well. Okay. And so the first thing to do is to normalize this, and you know that for a Gaussian wave, this is a completely real thing, so I can just say squared. Running from minus infinity to infinity. But this is, although this is a displaced Gaussian pattern, but that doesn't matter, right? I can make a change of variables from k minus k naught to say q, right? And then the integration limits still run from minus infinity to infinity. So really, we're concerned about an integral of the form like this. Okay. So now I think all of you probably know how to integrate a Gaussian. Okay. Does everybody know how to integrate this?
Not necessarily, I think.
Okay, so good. Let's talk about how to integrate this. So
you square.
Yeah, you square it. So I make 2 copies of this, and right now for this integration, this is mathematics. It doesn't matter if I call this k or x or whatever. So let's say I make 2 copies of this. Let's call this I. One copy. I'm considering I times I. Okay. And then I make another copy. Let's call that integration variable y. Okay. And now I'm sure that these integrals will converge, right? Because it's flying out like a Gaussian. So let me combine the 2 integrals. Okay. So now imagine x and y happens to represent a plane. X and y. So now the integration domain is what the entire plane, right? So I can change to polar coordinates. How do I integrate in polar coordinates? I go from 0 to 2 pi. Right? And then this, that's called the angle d theta. And then the other one, I go from 0 to infinity of r. Right? And then this integration changes to dr r times e to the minus r squared. Right? Okay, now this part is easier. That's just 2 pi. What about this here? Okay. So you make it also 0 to infinity. Okay. So that's 1/2 the r squared e to the minus r squared. Right? And this integral is easy. Okay. You're going to get a minus sign, and you 1/2 out e to the minus r squared. Value of it equal to 0. So in the end you get 1/2 for the radial part. And then you multiply by the angular part, you get I squared is equal to pi. So we get that the important Gaussian integral. Did I erase that? Okay. So this is equal to the square root of pi. Right? And then we think about inserting a scaling factor, which is to insert it over here. Okay. So we have a q delta k in this. So let me write that over here. So now if I inserted a scaling factor, as this is the integral of mean. Right? Okay. What's going to happen to the value of the integral if I insert a really large positive number here? Does the integral increase or decrease? Decrease. Right. So we know that the answer should be inversely proportional to that. So it turns out, okay, this is equal to square root of pi over delta k. Am I right? What?
We can just do another transform.
Yeah, I could. Yeah, let's do it. Let's do it. Okay. So where are we? So
You're right.
yeah, I think. So we do 2 copies of this, right? And what's going to happen is you're going to get a minus this thing on the minus r squared. So we're integrating this. Okay. So to get the whole factor out here, I want the r squared over delta k. That means it's necessary to multiply by delta k outside. Okay, and then of course there is the 1/2. Correct? Okay, and then this is no different from this now. Okay. So all this thing turns to 1/2. Right? Okay, so I missed so this is 1/2. So this goes into a half delta k, and then what I need is this pi here. So the angular is 2 pi. So I get delta k pi. Okay, so I was wrong. All right, so this integral should turn out to be square root of pi delta k. Okay,
So then how did you get q squared over the other 3 negative prime in the last line on this problem? You just plug that in, right?
Sorry. That should be delta k squared.
And then you have 2 multiplying e.
Yeah,
so
yeah,
that should be
yeah.
half 2 in the denominator still plus.
No, but I'm saying like you need to do
Square
this
it.
square. You need to square it.
Square, then you multiply by 2 in the exponent. That's a 4, right? Instead of
I'm
2.
sorry. Yeah. Okay, sorry. All right, but that doesn't change matters too much, right? We just need these factors here. So in the end, we get 2 delta k squared on the outside. Correct? Yeah. So I plug that in. This is the integral we're interested in. Okay, and this goes to delta k square root of 2 pi. Okay. Yep. Right. So now the correct, that means the correct normalization factor, because we're writing c squared. We're trying to find out how to normalize this. So the correct normalization factor will then be, sorry, this is not square root. Okay, I'm lost here. Okay, the correct normalization factor would be
1 over the square root of sine 1.
yeah. We need to square root that twice.
Yeah, that's right.
Something is wrong.
So it's square root 1 times.
And do remember things.
Okay, so it seems that the normalized, correctly normalized, okay. So now we have normalized the Gaussian wave packet. Okay, let's consider this Fourier transform. So that amounts to, okay, so you guys, when you go home, you might want to check this normalization factor. I'm a bit confused right now. I'm not sure if it's correct.
It's just the delta k squared, that extra square root of overall, you know.
Okay, yeah. Anyways, when we Fourier transform the Gaussian wave packet, okay, there's a multiplicative factor. Doesn't matter. So what's important is this one. So suppose that I have a Gaussian wave packet like this, and then I take its Fourier transform. This is a function of z factorial. Okay. So how do I do this? Well, the technique here is to complete the square. Okay? Because once you complete the square, then you can do a change of variables like this one. Right? Okay. So now the integrand is this. Right? It's exponential of minus k squared plus I k z. Okay, so let's take this to be minus k squared I k z. So how do I get how do I complete the square here? And because there's a minus sign here, right? So imagine this being k squared. Because this will be the okay. If I computed the square of this term, what would I get? I would get k squared minus I k z, right? And then I would have a minus z squared over 4, right? So that's how you complete the square here. Okay, so that amounts to k 2 minus sign gives you a plus, right? So you need to factor this by C squared over.
Maybe since they're running out of time
Oh,
to do the math, why didn't you just tell us the salient feature of if the math was to be done correctly? What
Yes, yes, if
what
the
would
math
you get
was
as
to be
the
done
salient feature of this?
correctly. So the idea is that the Fourier transform of a Gaussian remains a Gaussian. Okay. But what we have done is essentially correlated the width of the two Gaussians by this Fourier transform. Okay, so in the in position representation, that Gaussian that we have assembled might look like something like this. And then there's a certain width. Let's call this delta x. Okay. And then in the momentum representation, the Gaussian looks similar. Okay. And then there's a width delta k. Okay, now if we did the calculation, if we carried out the calculation, we will find this. Delta x, delta k is exactly 1/2. Okay, which means that if I plug in the Broglie's relation, delta x, delta p is h bar over 2. So it says that for a wave packet localized to with when I sum up different waves with different momentum, I get a localized wave packet to within the uncertainty of delta x. So a localized wave packet to within delta x is going to have an uncertainty in the momentum of delta p, and delta x, delta p is h bar over 2. So this is a specific case of the uncertainty principle. And the general statement, which we cannot derive right now, is delta x, delta p is greater than or equal to h bar over 2. Okay. So actually the Gaussian wave packet is what's called a minimum uncertainty packet. Okay. So the salient features are here. Oh, okay. So I guess this does conclude this lecture, and next lecture I guess we'll start by correctly going through the math here.
Yeah, I think the math, you probably have seen this in other courses.